So today we're going to learn about arithmetic and geometric sequences. So a sequence is just a list of numbers in a particular order. So I gave you an example. So this first example, I gave you 3, 6, 9, and 12. So to go from 3 to 6, you can add 3. To go from 6 to 9, you're going to add 3. To go from 9 to 12, you can add 3. So this is actually an example of an arithmetic sequence, which we'll talk about in a second. So in a sequence, the first term is A1, the second term is A2, and so on. So you can have A3, A4, A5, forever and ever. Many sequences have patterns. The two types of sequences that we will be studying are arithmetic and geometric. So let's look at arithmetic sequences first. So an arithmetic sequence is a sequence where each term is found by adding a constant to the previous term. This constant is called the common difference. So example number 1. Find the common difference of 3, 6, 9, and 12. So how can we go from 3 to 6? We can add 3. How can we go from 6 to 9? We can add 3. How can we go from 9 to 12? We can add 3. Now, for an arithmetic sequence, they all have to be the same common difference. So we had to add 3 each time to get the next term. They can't be different. In this example, our common difference will be 3. This is an arithmetic sequence. Okay, let's look at the next example. So find the common difference of the following sequence: 55, 49, and 43. 55, 49, 43. How can we go from 55 to 49? We can subtract 6. How can we go from 49 to 43? We can subtract 6. So this is going to be an example of an arithmetic sequence with a common difference of -6. So let's take a detour and look at two different types of formulas. There's recursive formulas and explicit formulas. In a recursive formula, each term is found by doing something to the term that's immediately in front of that term. So it has to be the one that's directly in front of it. For example, take the arithmetic sequence 2, 4, 6, 8. Each term is found by adding what to the term before it? So to go from 2 to 4, what do we add? 4 to 6, what do we add? 6 to 8, what are we going to add? It's going to be 2, right? We're going to add 2. So a recursive formula for this sequence would be a subscript n equals a subscript n minus 1 plus 2. Let's check to make sure this recursive formula would be right. So we have 2, 4, 6, 8. That's our sequence. And if we were to label, this would be A1, 4 would be A2, 6 would be A3, 8 would be A4. So let's check to make sure that this formula will give us A2. So our formula will be A to the 2 minus 1 plus 2, which gives us A1 plus 2. And what is A1? A1 is 2. So we'll have 2 plus 2, which is 4. And is A2 4? Yes. So it worked. Now let's try A3 just to make sure we have the hang of this. So A3 would be A to the 3 minus 1 plus 2, which will give me A2 plus 2. And what is A2? A2 is 4. So we'll have 4 plus 2, which is 6. And is A3 6? Yes. Okay. So let's use this recursive formula to find a to the 6. I'm just going to copy this down again. So our recursive formula is a subscript n minus 1 plus 2. And we're using 2, 4, 6, 8. We have A1, A2, A3, and A4. So we need to find A6. So for our recursive formula, we're going to need to know the term that's directly in front of it. But do we know A5? No. The highest term that we know is A4. So that's where we've got to start. So we can use A4 to find A5. So A5 is going to be A4 plus 2. A4 is 8 plus 2, so A5 is 10. Now we can use A5 to find A6. So A6 will be A5 plus 2. A5 is 10 plus 2 gives me 12. So A6 will be 12. Now, could we use this formula to find a to the 100th? Yes. What would we need to know in order to find a to the 100th? We would need to know the term that's directly in front of it, right? Which would be a to the 99. A subscript 99. So what are some drawbacks that you can see to recursive formulas? First, they can get time consuming, because you're always going to have to know the term that's directly in front of it. So there's no skipping terms, which leads back to the time consuming problem. So thankfully, there are explicit formulas. And an explicit formula helps you to find any term in a sequence quickly, as long as you know the very first term. So for a recursive, you had to know the one that's directly in front of it. But for explicit, all you need to know is that first term to write a formula, and then you can find any term that you want to. Alright, so the explicit formula for an arithmetic sequence is a to the n equals a1 plus d times n minus 1. a1 is the first term, n is the number of term that you are looking for, and d is the common difference, which we've talked about. So let's look at this first example. Write an equation for the nth term of the arithmetic sequence 8, 17, 26, and 35. So first, let's just check to make sure it is arithmetic. How can we get from 8 to 17? We can add 9. How can we get from 17 to 26? Add 9. 26 to 35, add 9 as well. So it is going to be an arithmetic sequence. And they want us to find the nth term. We're going to use an explicit formula. So the formula for an explicit we're going to have a to the n equals a1 plus d times n minus 1. So we're going to need to know a1, which is our first term. What's our first term? 8. What is our common difference? 9. And we're not going to worry about the n right now because we want to know the nth term. We're not looking for a specific term. So if we plug that in, we'll have a to the n equals our first term, which is 8, plus 9 times n minus 1. This would be our answer. So if you know the formula, it's pretty simple. Let's try another one. So write an explicit equation for the nth term of the sequence 1.3, 3.8, and 6.3. Let's see if it's an arithmetic sequence. So to get from 1.3 to 3.8, what can we do? We can add 2.5. To get from 3.8 to 6.3, what can we do? Add 2.5. So this is an arithmetic sequence. So we know in order to use that explicit formula, we're going to have a to the 1 plus d times n minus 1. What is our first term? 1.3. What is our common difference? 2.5. And we simply plug that into our equation. So the nth term will equal 1.3 plus 2.5 times n minus 1. This is our answer. Now we can use our knowledge of creating explicit formulas to find any term that we want to. So find the 50th term for the sequence 31, 24, and 17. So anytime they ask you to find a term this large, it's probably going to be easier to use the explicit formulas because I don't want to use this sequence to go all the way to the 49th term to use my recursive formula. I just want to use one formula that'll work all the time. So let's see if we have an arithmetic sequence. To go from 31 to 24, what do? Subtract 7. From go to 24 to 17, we subtract 7. So we do have an arithmetic sequence. So we know we can use the explicit formula a subscript n equals a1 plus, keep on writing that wrong, d times n minus 1. So what is our first term? 31. What is our d? Negative 7. And this time we're looking for that specific term number. So our n will be 50. So we'll have 31 plus, not plus, it's a negative, negative 7, 50 minus 1. So 31 minus 7 times 49, which will give us negative 312. So our 50th term for that sequence will be negative 312. Given the sequence defined by the function a n plus 1 equals a n plus 12, with a1 equals 4, write an explicit function rule. So the wording of this looks a little scary, but it's not as bad as it seems. So they give us a formula for our sequence instead of just giving it to us. They tell us our first term is 4. So let's write 4 down. Then they tell us here how to find each succeeding term. So right here it says a to the n plus 12. So we can simply add 12 to 4. So 4 plus 12 gives us 16. Add 12 again to get the next term, 28. Add 12 again to get the next term, 40. And you can keep on going forever. I'm going to stop there. So write an explicit function rule. So now that we have our sequence, everything's the same. We can use this sequence to write our explicit function. So what's our first term? 4. What's our d? 12. To go from here to here, you add 12. Same with the rest. And we're not looking for a specific n. So remember that formula. So it's just going to be our first term, which is 4, plus 12 times n minus 1. And that's it. It was just worded a little differently. Alright, so now let's talk about geometric sequences. So a geometric sequence is a sequence where each term is found by multiplying the previous term by a constant. And this time it's called the common ratio. So we're multiplying instead of adding, and it's called the common ratio instead of the common difference. So we can find the common ratio by dividing any term by its previous term. So example 5, find the common ratio of the following sequence: 8, 20, 50, 125. So we can take 20 divided by 8, which gives me 2.5. Now let's check the next set. So 50 divided by 20. Is that 2.5? Yes. And then the next set, 125 divided by 50. That's 2.5. So this is a geometric sequence, and the common ratio, so instead of d, we have r now, is 2.5. Let's look at another one. Find the common ratio of 1.25, negative 1.5, and 1.8. So we'll take the second term divided by the first term. So we have negative 1.5 divided by 1.25. That gives me negative 1.2. Let's try the next set. So the third term, which is 1.8, divided by 1.25 gives us negative 1.2. So this is a geometric sequence with a common ratio of negative 1.2. Let's try one more. So find the common ratio of 405, 135, and 45. So 135 divided by 405. Now, for these, you have to make sure you get a fraction. So if you get a decimal on your calculator, hit Math Enter Enter. So 135 divided by 405, Math Enter Enter, you should get 1/3. And let's check the next set. So the third term divided by the second term equals Math Enter Enter, it's 1/3. So our r is 1/3. It's a geometric sequence. Okay, let's go back to recursive formula. So this time we're going to write a recursive formula for a geometric sequence. So we need to find our common ratio. So to go from 3 to 6, what can we multiply? We can multiply by 2. To go from 6 to 12, what can we multiply by? 2. 12 to 24 is 2. 24 to 48, 2. 48 to 96 is 2. So our common ratio is 2. So recursive, remember for recursive, we have to use that previous term every time. So we'll have a to the n will equal the previous term times 2. And that's it. Your new term will equal the previous term times your common ratio. That's how you write the recursive formula. Okay, write a recursive formula for the following sequence: 81, 108, and 144. So we have 81, 108, 144. What is our r? So 108 divided by 81 is what? should give you 4/3. And try the next set. So 144 divided by 108 gives us 4/3. So our R is 4/3. Okay, so our recursive formula is our new term will equal our previous term times 4/3. Now they wanted us to use this formula to find the fifth term. So I'm going to do this in this box here. So 81 is our first term, 82 is our second, or 82, 108 is our second, and 144 is our third. So in order to find our fourth, we can use our formula. So a fourth will be its previous term, which is A3, which is 144, times 4/3, which gives us 192. So a to the fifth will be a to the fourth, I'll write a to the fourth, times 4/3. A to the fourth is 192 times 4/3, and that will give you 256. So our fifth term will be 256. So like arithmetic sequences, we have explicit formulas for geometric sequences. So for the explicit formula for a geometric sequence is a(n) equals a1 times r to the n minus 1, where a1 is your first term, n is the number of term you are looking for, and r is your common ratio. Let's look at an example. So write an equation for the nth term of the geometric sequence 3, 12, 48, and 192. So to go from 3 to 12, 12 to 48, and 48 to 192, what are we multiplying by? We're multiplying by 4. So a to the n equals a1 times r to the n minus 1. We're just going to plug in what's missing. So our first term is 3. Our r is 4. So we'll have 3 times 4 to the n minus 1. That's your equation. Okay, let's look at another one. Write an equation for the nth term of the geometric sequence 4, 6, 9, 13.5. So we know we're going to use the equation a1 times r to the n minus 1. Our a1 is 4. What is our r? So if we take the second term divided by the first term, that gives us 1.5. If we take the third term divided by the second term, that gives us 1.5. Third term divided by the second term gives us 1.5. So our r is going to be 1.5. Remember, it has to be the same for all of the terms. So a1 is 4 times 1.5. Remember, I want this as a fraction, which is 3/2. Oops. N minus 1. That's your answer. 4 times 3/2 n minus 1. Find the eighth term of a geometric sequence for which a1 equals -3 and r equals -2. So we have our equation an equals a1 times r to the n minus 1. So let's write our equation first. a1, our first term, is negative 3 times negative 2 to the n minus 1. Now make sure you keep these separate. So the negative 3 needs to be separate from this negative 2 to the n minus 1. Do not combine them. It'll mess you up. So we're trying to find the 8th term. So we're going to have negative 3 times negative 2 to the 8 minus 1. Keep on bringing everything down. So negative 3 times negative 2 to the 7th. Now, just find negative 2 to the 7th first. So we'll have negative 3 times negative 2 to the 7th is negative 128. Now we can multiply these two together. So negative 3 times negative 128 is 384. Last problem for today. So given the sequence defined by the function a(n plus 1) equals 3/4 a(n) with a1 equal 424, write an explicit function rule. So it's very similar to the last problem for the arithmetic sequences. It looks complicated, but it's really not that bad. So we're starting with 424, and then this equation tells us how to get to the next one, to our next term. So we're going to multiply by 3/4. So what is 424 times 3/4? You should get 318. What is 318 times 3/4? You should get 238.5. And you could keep on going forever, but I'm going to stop. So in order to write our explicit function rule, we need to know our a1, which is, what's our first term? 424. And we need to know our common ratio, which is the 3/4. So our a(n) will equal 424 times the 3/4 n minus 1. And that's your answer.